My name's Josh. I'll give our presentation, and then like Bath, we replaced our commercialization section with a bit of info about our leadership structure. So we are CBU Cardiac Engineering, a fully undergraduate team. Sorry, hold on. A fully undergraduate team of over 50 scientists and engineers from California Baptist University in Riverside, California. My name is Josh Lute. I'm the president. With me is Gianna Lawson and Jessica Gordon. They're also on the call and they'll be presenting. And then our advisor is Matthew Jared Card. So cardiovascular disease is the leading cause of death worldwide. And without a permanent solution, many are left without options. And it's true that by the end of this presentation, over 600 people will have died from cardiovascular disease. It's this statistic paired with over 3,000 patients in the US alone awaiting heart transplant that we aim to build the world's first permanent total artificial heart.
Within this year, we focused on 5 specific goals: how to optimize low power consumption, reduce blood damage, pump 5 liters a minute, create pulsatile motion with a stroke volume of 70 milliliters, and fit within the heart cavity.
Pulse by CBU Cardiac Engineering is a novel biventricular peristaltic pump. Pulse 1 was highly successful as it was able to output as high as 5.6 liters per minute and was awarded 3rd place at the Heart Hackathon last year. Through research and development, we've been able to make 4 new peristaltic pumps, which led to our new tubeless peristaltic pump, Pulse 3. Our Pulse 2.4 design is a highly effective pump with an accurate native pressure of 125 over 90 millimeters of mercury and impressive flow rates as high as 9.8 liters per minute and power draws as low as 7.2 watts.
However, without power, flow rate means nothing. We optimized our pump to be extremely power efficient. While Syncardia is able to pump 9 liters per minute at 40 watts, Pulse 2 pumps 10 liters per minute at 21 watts, making Pulse 2 twice as power efficient as Syncardia. The graph on the left shows power versus flow rate, showing how we increase in flow rate with power. We are able to draw power as low as 7.2 watts at 7 liters per minute. This is loosely comparable to Bivocor's power draw, ranging from 6 to 17 watts at 5 to 12 liters per minute. However, if you extrapolate the trend line to 5 liters per minute, you find that we have a theoretical power draw of 4 watts, which is lower than both.
This was all tested in our CBU Garner mock loop. The Garner MCL 1.1 included a compliance chamber, pressure, flow rate, and power measuring capabilities. MCL 2.1 is being designed as a biventricular MCL and will incorporate all components of the MCL 1.1.
The 2 requirements that we met with Pulse 2 is having low power consumption yet generating high flow rate. The 3 that remain have a common issue within our tubing element in Pulse. Looking into the tubing, we saw that there was many issues with our tubing, a couple being limited stroke volume and longevity issues. From this, we searched everywhere and we have not found tubing that met all of the needs of our pump. Therefore, we dove into custom tubing research. We created composite materials and tested them under a mechanical fatigue tester, and after degrading them, we saw that we needed a new solution for the tubing. So we dove into tubeless design exercise that took 3 months, where we created multiple tubeless pumps, outputting as high as 8 liters per minute. And from all of this research, we have been able to craft a tubeless peristaltic pump. We'd like to present to you Pulse 3.
Pulse 3 is a biventricular toroidal pump that uses a magnetically levitated shuttle to gently move blood with minimal resistance. The shuttle separates 2 chambers, enabling synchronized forward and back strokes for the systemic and pulmonary flows. Ductile valves control inflow and outflow, while neodymium magnets and a central rail guide shuttle movement, minimizing contact points and hemolysis risk. Finally, an internal PTFE coating reduces friction and thrombosis potential. Then, made out of a certified biocompatible material, Pulse 3 takes steps to align with ISO standard 10993 biocompatibility. Outputs as high as 3.4 liters per minute at 40 beats per minute, with 5.0 liters per minute projected at 60 beats per minute. This mimics the native heart stroke volume of 70 milliliters. Finally, we have an 83% ejection fraction for hemolysis purposes.
Qualitative preliminary CFD validation on our first Pulse 3 iteration has begun to test hemolytic capabilities and flow patterns. Blood damage is a factor of exposure time and shear force, which we estimate to be low. Pressure is seen in the figure, showing the exit points and the points of high and low pressure. The rail reduces contact points and decreases hemolysis points, and the shuttle gap size within the housing will be iterated to balance flow rate and blood damage. To validate our low blood damage, hemolysis testing was started. This year, we were able to run 6 bovine proof of concept tests on Pulse 1, aiming to comply with the ASTM standards. Through centrifuging and separating red blood cells and plasma, we can measure the release of hemoglobin within the separated plasma. As peristaltic pumps have high blood damage, our new novel pump will decrease this challenging issue in industry today. Each model of Pulse has made steps towards getting smaller. Pulse 3 is 3 times as small as Pulse 2, with double the stroke volume. Pulse 3 is also half the size of the native heart, with the same stroke volume.
From this, Pulse 3 meets all key design requirements. Its frictionless maglev system ensures low power consumption and minimal blood damage. The projected flow rate mimics that of the native heart, achieving pulsatile flow with 70 milliliter stroke volume. And at 318 milliliters, we easily fit within the pericardial cavity. Beyond the pump, Pulse is connected to a holistic electrical system. Novelty is in every component. From the custom battery array to our app, CB Cardiac is building the most advanced electrical system they can. As percutaneous driveline infection is the #1 reason for patient readmittance, we have officially partnered with Invivo Power to build a highly effective TET link. Utilizing a toroidal ring instead of a parallel plate, Invivo TET maximizes power efficiency, minimizing heat generation. We're able to output as high as 30 watts of power at 95% efficiency, making us 3 times as power efficient as commercially available resonant link. To address power needs, we're developing biocells to convert internal energy to electrical energy, aiming for a fully self-contained pulse within 5 to 10 years. Meanwhile, a flexible Kirigami-based battery array offers 24-hour charge, wearable on the arm, waist, or leg, with an internal emergency battery for disconnection situations. Finally, our app, Pulsefinity, is good for daily data logging for doctors, oxygen concentration, flow rate adjustment, and automatic emergency assistance.
Some of the limitations that we've encountered include limited CFD. This is due to a lack of infrastructure. We are currently building our CFD simulations for hemolysis, pressure, and fluid flow. Another limitation is our magnetic levitation system is limiting our flow rate. This is due to magnet slipping, and this is being mitigated by our Hallback array. And finally, for our mock loop, we are using water validation for all of our flow rate calculations instead of a viscous fluid.
Our pump will progress through component level improvements. Magnet slipping was the main issue for our limited flow rate, so we will decrease the gap between each magnet and introduce a Hallback array to mitigate this. We will also use mechanical low hemolytic valves, such as the Medtronic open leaflet valve. We're also developing our own custom tri-leaflet valves, and we will compare the efficacy of both. Next generation Pulse will be optimized for anatomical fitment using Vertana EV patient, and hemolytic simulation CFD will be used. All of this brings us to a technology readiness level of 5.
Our magnetic levitation system will both suspend and drive the shuttle autonomously without the need for a motor. A proof of concept linear rail is currently being manufactured, which is capable of moving the shuttle in an oscillating motion, and this brings the project to a technology readiness level of 2.
Okay, so now I'm going to talk about our leadership style, what we did, and how that worked for us. So the main thing that we have is president, vice president. This was something that we adopted from some of our other teams on the university, and it's something that we really like. This is kind of comparable to team lead and co-lead, but we put a lot of care into choosing the vice president because we hope that they would replace the president, and it just kind of gives them a trial period. Knowledge transfer is also really important, and so by giving the vice president as much time as possible to kind of soak up from the president, it offers knowledge transfer. We also end our season after Japan, and so then that gives us a whole semester and a half for the president to be senior advisor and then vice president to become president. And so it kind of gives a buffer before and after for vice president coming into their new role. Under the president vice president, we started with 4 sub teams: electrical, mechanical, research, and business. However, as our team grew, we started with only 6 members, and then we grew to now over 50. We had to kind of grow our leadership with our team as well. So looking at this year, this is what our leadership looks like right now. This year we have one general weekly meeting with each sub team has to meet on their own specifically, and then we have a leads meeting as well. So the president vice president is then delineated into systems, so the design, research, and PR system, which are then delineated further into the mechanical and electrical teams. And then under that are projects. And so a project lead would be in charge of valves, pumps, CFD, or hemolysis. And then they report to like the mechanical team lead and then the design system lead.
For future leadership, it's pretty similar to how we have Pulse 3. We're just changing a couple of things. We now have design as its own sub-team. So as you can see, we have mechanical, including projects such as the pump, materials, and all of our in vivo test benches. We have design as our future CAD, and this is more for anatomical fitment, as well as all of our in silico testing, which is CFD and FEA. For electrical, we are continuing with our maglev system, battery and control system, and this will also go hand in hand with all of our test benches. And finally, we have our research team working on hemolysis, as well as our blood loop, and researching energy harvesting, as well as documenting all of our research within what we like to call the Heart Bible. So thank you, and thank you to all of our sponsors and all of our advisors.